And if you're like me, you'll probably like this lesson a little bit more than the last one. I don't really enjoy doing all of the transformation things on graphs. I think that gets a little tedious after a while. A lot of this lesson deals with more algebraic type of math. We're looking at solving exponential equations, and this, again, this is on page 8 of your unit handout. We're doing basically two things in this lesson. We are going to be solving exponential equations, and there will be a couple of different ways that we can do that. We can do it algebraically, or we can do it graphically, and we'll talk about why you would do one and not the other in a bit. But then we're also going to be looking at more exponential growth and decay. Particularly, we're going to look at investments today. When you invest money into a bank account, you're paid something called compound interest, which is a type of exponential growth. So to begin with, what an exponential equation is, everybody, is an equation, so it's got an equal sign, and it contains the variable that you want to solve for as part of the exponent. So whenever you are trying to solve an equation where the exponent contains what you're after, that's considered an exponential equation. And there's really no build-up to this. We're just going to take a look at how we can solve some of them. The first thing I want you to note is that example 1 is not an example that I would give you on an exam, even a multiple choice question. It's too simple. It may not be simple for you right now, but it will be simple after I explain what's going on here. 7 raised to the 4x minus 5 is equal to 7 raised to the 2x plus 3. Well, if you think about that, the only logical conclusion that you can come to is that these two exponents have to be equal to each other. You know, if the exponent on the left happens to be 5, then the left side would be 7 to the 5. But if that's equal to 7 to another exponent, that other exponent must be 5 as well. The reasoning here is that we go from this equation to this equation, but we don't do that because we're dividing both sides by 7 or we're canceling the 7 somehow. We do that for a logical reason. If 7 raised to one quantity is equal to 7 raised to another quantity, those two quantities have to be equal because the bases are equal. And then we solve this equation. I subtract 2x from both sides to get 4x on the left side. I add 5 to both sides to get 8 on the right side. And I get x equals 8 over 2, which is 4. So as I said, this example is just there to illustrate to you that if the bases are the same, then the exponents must be the same. So what we had in this question, A, is a common base of 7. It was common. Both sides had it. Any questions or comments on 1A? All right. So 1B is 3 to the 3x plus 1 equals 81. And we want to build a common base. Now, one of the bases is 3. The base on the left side is 3. The base on the right side is 81. So we want to write both of these using the same base. So for example, maybe, it's not the case, but I'm just explaining to you the thought process. Maybe 3 can be written as 2 raised to an exponent, and 81 can also be written as 2 raised to an exponent. If we could do that, then they would both be in base 2. Well, 3 cannot be written as 2 raised to an exponent because 3 is a prime number. The fact of the matter is 3 is 3 to the 1. So can we write 81 as a power of 3? In other words, use your calculator and see if you can find a number to which you would raise 3 to get 81. And I'm sure by now many of you have found it. Can you tell me what that number is? It's 4, right? 3 raised to the 4. So 81 is the same as 3 to the 4. And what is going to happen, hopefully this is the goal, is that when you see certain numbers, like 81 in your head, you go, oh, that's 3 to the 4. When you see 27, you go, oh, that's 3 cubed. When you see 16, you're going to go, oh, you know what, that's 2 to the 4. There are going to be some of these numbers that we see so often that you're not going to have to go to your calculator each time. Bottom line here is, since 81 is 3 to the 4, we can rewrite this equation as 3 to the 3x plus 1 equals 3 to the 4. And now we use that reasoning that I talked about in A. If the bases are both 3, if the bases are both 3, then the exponents must be equal as well. So that means 3x plus 1 equals 4. And now, you know, it's a grade 5 question. Conceptually anyway, you subtract 1 from both sides, and then you divide both sides by the coefficient of x, and you get x equals 1. I would probably say to you that this question is still not a question you would see on an exam. It's too simple. We're warming up to the Math 30 stuff. But any questions with B? All right, 36 raised to the 2 minus 3x is equal to 216 raised to the x. So your job, and I'm going to give everybody a few minutes here, is to come up with a base for both of these. Where the base is the same. Where this base and this base is the same. The exponents don't have to be the same. Clearly they won't be the same. But I want you to come up with the common base. What base can we use? Some of you might say, well, maybe this is like the previous question. Maybe 216 is a power of 36. And you would go to your calculator and say, well, let's see, maybe, I hope most of you don't, most of you see this can't be, but maybe 36 squared is 216. No, way too big. So yeah, it is in fact going to be 6. As soon as you discover that the smallest number is not the common base, then you start asking yourself, how can I write 36? And in terms of exponents, there's only one way that you can write 36. It's 6 squared. So then you say to yourself, well, maybe 216 is a power of 6. And you try, well, I hope you wouldn't try 6 squared because you get 36, but you try 6 cubed and you discover that it's 6 cubed. So what I'm going to do in this equation is where I see 36, I'm going to put 6 squared. And notice I put the squared inside of the brackets. It's raised to the 2 minus 3x. And where I see 216, I'm going to put 6 cubed, and it's raised to the x. Now we can't drop the exponents yet. What we need to do is go back to grade 9 and 10 math and remember something. When you have a base raised to an exponent and the whole power is raised to an exponent, that's called a power of a power, and it's simplified by multiplying the exponents. For example, x squared cubed is x to the 6. And I could demonstrate that to you because x squared is x squared. Cubed means x squared times x squared times x squared, which is x times x. That's 1x squared. Here's my second x squared. Here's my third x squared. Well, I have 6 of them, which is x to the 6. So whenever you have a power of a power, you multiply the exponents. And that means that on the left side, we're going to have 6 raised to the 2 multiplied by 2 minus 3x. And on the right side, we're going to have 6 raised to the 3 multiplied by x. I'm multiplying this and this to get that. And I'm multiplying these two to get that. Now we can drop the exponents. You could multiply that stuff out first if you wanted to. Let me show you what I'm referring to here. You could now say 6 to the 4 minus 6x equals 6 to the 3x. Right, I'm multiplying through. And then you could drop the exponents and get that. I think, everybody, if you go from here to here, I think that's a bad idea. I think it's a bad idea because it opens up room for you to make mistakes. But I believe on a written response, you need to show what's happening. So you can either go from here to here and then to here, or I guess you could go from here to here and then to there, but you need to show the fact that you are multiplying the exponents. Anyway, the rest of this question is child's play. That means it's very easy. We have 4 minus 3 minus 6x equals 3x, which means we have 4 equals 9x. You divide both sides by 9, not by 4, by the coefficient of x, and we get x equals 4/9. And by the way, there's no reason for you to check for extraneous roots in these types of questions. Any questions with this one? C? All right, let's take a look at D. Since, I don't know, things that are obvious to me, I realize are not always obvious to everybody else. But since one of the bases is 5, and 5 is a prime number, which means you can't write it as a power of anything other than itself to the 1, that must mean the common base has to be 5. You can't write 5 as 2 to the something or 3 to the something. So we have 2 little exercises that need to be completed. 625 is 5 raised to the what? And root 5 is 5 raised to the what? We need to know the exponents on the 5s that would give us the 625 and the root 5. Well, you can play around on your calculator. Correct me if I'm wrong. 5 to the 4 is 625. Is that right? 5 to the 4? Okay. Okay, that's easy. So we're going to rewrite this so far as 5 to the x equals 5 to the 4 times, now what do you raise 5 to get the square root of 5? 1/2. We need to remember, this is from, I believe, Math 10. I'm pretty sure it's Math 10. That a square root is equivalent to a power of 1/2. This isn't a mathematical proof, but I mean, if I take the square root of 5, I get that number. If I take 5 and raise to the 1/2, which, by the way, if you're going to raise it to the 1/2, you better put a set of brackets there. Anyway, you get the same thing. So then we have 5 to the 4 multiplied by 5 to the 1/2. And here's the biggest mistake that's made. We bring this stuff together and we get 5 to the x equals 5 to the what? What will we get when we combine 5 to the 4 multiplied by 5 to the half? And a lot of people will say 5 to the 2 because 4 times a half is 2. It's actually 9 halves. Because there's a lot at stake here from grade 9, 10, and 11 math. When you have a base, I'll use r, and it's raised to a number like 5, and you multiply by that same base raised to a number of, say, 4, the rule is you add the exponents. So I need to take 4 plus a half. And I believe 4 plus a half, well, I know it's 4 1/2, which is 9 over 2. And now we have the base is the same, so we can drop the exponents and say x equals 9 halves. Any questions with D? All right. So are there other ways you can solve these? Well, for example, if you look at question 2, you have 25.8 equals 3 to the x, and the fact of the matter is there is no common base in the universe we can use. Well, not in high school math. There is an algebraic way to find the answer here, but you will not learn of it for a couple of days. So we're going to use what your textbook calls systematic trial, and I think this is the worst method in the universe in this course. But for some people, it might be their only hope. What you're basically going to do here is ask yourself what x could be. Could x be 1? Well, no, because 3 to the 1 gives you 3. It doesn't give you 25.8. Could x be 2? Well, no, because that would give you 9. Could x be 3? Well, no, but notice that when x is 2, we get 9, and when x is 3, we get 27. We want to get 25.8, which is pretty darn close to 27. So then what you do, and I really hate this method. When I say it's clunky, I mean it's clunky. Then you go, well, maybe it's 3 raised to the 2.9. I don't know. No. Maybe it's 3 raised to the 2.99. Not quite. Do you see, or too much now, actually. So maybe it's 3 raised to the 2.95. Do you see where I'm going with this? I'm going to get some feedback here that you guys get what I'm doing here. Okay, and I hope you get how ridiculously clunky it is. I'm not going to spend a bunch of time with this, and don't worry about what I'm doing. Don't try to figure out what I'm doing. But I will tell you right now that if you hammer away at your calculator long enough here, you will discover that this is the number that works the best, okay? This is the number that works the best. If I were to take 3 raised to that, I get 25.8. It's a trick that you will learn about, but there's a mathematical basis behind what I did. So by trial and error, you can kind of nail it down. This is so clunky and unimportant that I don't even want to do this question. Let's omit B. It's not something I would recommend doing. If you were absolutely stuck, go for it. But on a numerical response question, it would take you forever. Let's take a look at solving graphically. This is simple. If 12 equals 2/3 to the x over 4, then I suppose I can graph 12, and I can graph 2/3 raised to the x over 4, and find out where they intersect. There's no common base between 12 and 2/3. It is helpful here, everybody, for you to reach back into lesson 7.1 and understand that this graph is a decreasing exponential function because the base is smaller than 1. And it will have a y-intercept of 1. This graph is at y equals 12. They're going to intersect someplace in the negative numbers for x. So when I set up my windows for x and y, I would probably go, well, you need to go up to at least 12 for y, so you can see that y equals 12. But maybe negative 10 to 10 for x is enough. Well, let's find out. Here's the 12. No, not even close. These graphs are intersecting way, way back there. So I'm going to change the negative 10 for my x to negative 35. And you know, I don't know what the answer is. But when I graph, now all we have to do is find the intersection point. So negative 24.5 to the nearest 10th. We're going to omit the next question. I have to really focus on keeping on track here because I would normally say, well, it'll only take us a minute, and then next thing you know, 10 minutes have gone by. If you were to graph y1 equals the left side and y2 equals the right side, you would be able to find out the point of intersection, and the x coordinate of that point would be the solution to the equation. Does anybody have any questions about the stuff we're doing in examples 2 or 3, which is systematic trial and error or solving graphically? All right, so now we're going to look at one more application. When money is invested, you get something called compound interest. And what that means is that you start off with a certain amount of money. You have this much money, and the money sits in an account for a period of time. And then a little period of time later, at some point, maybe it's after 6 months, maybe it's after a year, you get a certain percentage of what you started off with. And let's say that that's 20%. So this piece right here is 20% of this piece. And then what happens is your investment, which now is bigger, sits in an account for the same period of time, and then at the end of that period of time, you get some money. And the money you get here in green is bigger than the money you got in red on the second diagram. And it's because the money you get in green is 20% of this, which is more money than you started off with to get the 20% of the red. So what happens is you get 20% of this the first go around, then you get 20% of this, then you get 20% of this. Well, that means it's exponential with a common base of 1.2. Not common. There's nothing, well, I guess it's common from one multiplication to another. And that's what compound interest is. When we solve compound interest, I've explained this, when we solve compound interest problems in this course, we use the same formula that is on your formula sheet that I've already talked about. So we're going to do a couple of questions using that formula. Just let me know, can somebody type yes or no? Is this in the lesson right on the same page that we're working on? Okay. So what's going on here? Jerry has found $10,000, well, he didn't find it, but all of a sudden he's got $10,000 he doesn't know what to do with. He puts it into an account that pays 8% per annum. That means 8% per year. And you will no longer be told per year. Per annum means per year. We need to know that. It's compounded annually. I'll explain what that means in a second. How much is in the account after 14 years? Remember what I told you. Try to remember what I told you about this formula. It's y equals a times b raised to the t over p and y and t are the variables. So in this particular case, what we are looking at we're not going to solve this graphically, but I think it's helpful to visualize it graphically. We are looking at this where your y is the money. So to come up with an equation that we're going to use, we have to come up with the values of these three parameters. A equals something, B equals something, P equals something. So what does it mean to say that he gets interest compounded annually? What it means is that on January 1st, he puts the $10,000 into the account. 10K goes out of his pocket and into the account on January 1st, 2021. And if he were to log into his bank account and look and see how much is there in August, he would see $10,000. I better not do that. He would see that there's $10,000 all year long. That's how much is in there. And then on December 31st, 2021, cha-ching, 8% is added. That's what compounded annually means. It means he doesn't get interest all the time. He gets interest once every year. And that makes our job easier because when you look at what P is the length of time it takes to happen. And it takes a year to happen. B is how much his money is being multiplied by regularly. Well, it's 1.08. Because what happens is he has 100%, and we add 8% to that, which is 108%. And to go back to elementary school for a second, percent means divided by 100. So 108 divided by 100 is 1.08. A is the initial amount, which is 10,000. So the equation we come up with is y is equal to 10,000 times 1.08 raised to the t over 1. I want to pause there. Any questions in getting that equation? Notice that t is 14 years. This is really the question here. When t is 14 years, what's the amount of money? Notice I don't put the variable value in. I want you to get into the habit of coming up with the equation first. Now we can go ahead and load in the time. And by the way, there's no need to write t over 1. I'll dispense with the different colors now. The amount of money will be 10,000 times 1.08 to the 14. So we can run that through your calculator, and by the way, I hope you know, it doesn't mean we're going to multiply 10,000 by 1.08 and then raise it to the 14. The order of operations is we do the exponent first. But our calculator knows that. So we don't even have to worry about doing it in steps. 10,000 times 1.08 to the 14 is this amount of money. So the answer to the first part of question 4 is $29,371.94. How much interest was earned? Well, we would subtract off his original investment. So the balance in the account at the end of the 14 years is $29,371.94. He earned $19,371.94 in interest. Interest is how much got added on throughout the 14 years. Does anybody have any questions with example 4? All right, number 5. Elaine also has come into $10,000. And she's going to invest it, but she's got a different account. And the difference here, everything is identical. Elaine invests $10,000, so did Jerry. Elaine got 8% per year interest, so did Jerry. Elaine invests it for 14 years, so did Jerry. What's different is that it's compounded quarterly. And we need to talk about what that means. So if this rectangle represents a year, and you were told that she gets 8% per annum, then the simple fact of the matter is she gets 8% per year. She will get 8% per year. But since it's compounded quarterly, the bank takes that 8% and says, we're not going to give it to you all at the end of the year. We're going to give you some money, some interest every quarter of a year. But since it's 8% per year, they're not going to give her 8% every quarter of a year. They're going to give her 2% here, 2% here, 2% here, and 2% here. And if it were compounded monthly, then to find out what percent you would get regularly, you would take that 8% and divide by 12. If it's compounded semi-annually, then we would get 2 chunks of 6. Now what this is telling us is that B is 1.02. Her investments gets multiplied by 1.02 here. It gets multiplied by 1.02 here, etc. So it gets 2% gets added regularly. The initial amount is still 10,000. I would like to give you an opportunity here to figure out what we're going to use for P. If you look at the top of the page, P is the length of time it takes to get interest. Anybody want to volunteer an answer in the message window? 0.25, 0.25. I need to ask you a question. 0.25 what? Years, exactly. So that's going to become important. I don't know if we're going to have time today for me to explain it in detail, but we're going to say 0.25 years. Did anybody think 3 months? Because you could put 3 months there. I wouldn't, but you could. So what is the formula going to be? The formula is going to be Y, the amount of money in the account, is the initial amount A. I'm just following that general formula at the top of this page you're looking at, times 1.02 raised to the t over 0.25. So in order for us to find out how much money she will have, we're just going to load 14 years in there. Incidentally, when you take 14 divided by 0.25, if you were to calculate 14 divided by 0.25, you'd get 56. And that's how many times she gets interest throughout the whole investment. Anyway, this is the amount of money that she has as a balance in the account. And if we subtract her initial investment, This is the amount of interest that she earned. Any questions with 4 or 5 now? I suppose it's worthwhile to note that Elaine earned more money. Getting the same interest rate divvied up into smaller pieces, but you get those pieces earlier and more often, is a better thing. All right, so now what we want to do is the final question of this lesson. Here's Jerry's money. Jerry's money is equal to 10,000 times 1.08 raised to the t. Elaine's money is equal to 10,000. I hope you're fine with me using J and E instead of Y for both, times 1.02 raised to the t over 0.25. The question is, if Elaine or Jerry, I better do this separately. If Jerry's money is 40,000, what's the time? If Elaine's money is 40,000, what's the time? And I'll tell you right now, I'm going to erase something here and then I'll put it back. This is the equation you're trying to solve. But this is an exponential equation because the variable is part of the exponent. You cannot solve this with a common base, so we have to solve it graphically. So we have to graph for Jerry y equals 40,000. And y equals 10,000 multiplied by 1.08 raised to the x. Clearly for our window settings, we're going to have to go up to at least 40,000. I'm going to go up to 50,000 for y. If you want to know approximately what to go up to for x, you could go to your table and start scrolling around. You know, my table happens to be right around 17, but you can see we've actually got the answer here. It's going to be 19 years, but we'll talk about that in detail. So I'm going to go up to 20 for x. I'm going to pause there to see if anybody has any questions about me choosing those window settings. Okay, so I graph. There's the 40K. Here comes Jerry's investment. It's exponential growth, so it's getting steeper and steeper and steeper as time goes on. When I find the intersection point, I get 18.01. Okay. Let's just leave that for a second. Well, no, let's deal with it. What should I write? What should I write for an answer? How should I round this? Because I wasn't told how to round it. But I need to round it a certain way if I'm going to get the question right. Exactly. I got to go 19. 18. If I round down, he will not have 40,000 yet. He only gets interest, you know, that 0.01 might be January 3rd of the year, but he doesn't get interest till the end of the year. So we have to round it to 19 years. Now let's do Elaine's. And this is going to be pretty easy. I can just edit my equation to be 1.02. Careful here, the exponent is x over 0.25. I need to put that x over 0.25 in brackets. Notice Elaine's is climbing quicker. I think it is. I'm going to double check to make sure I've entered it 1.02, yeah, that looks okay. So now I find the intersection point. Well, I'll pause there. Are we okay with that graph? Are you getting a similar looking thing? Okay. I thought it would be even steeper, but that's okay. Now what I want to do is calculate and I get 17.501. Well, I guess I don't want to circle it yet. I get 17.501. Go ahead and type in the chat window what I should record as an answer. Yeah, it's 17.75 because Elaine gets interest every 0.25 of a year. So you always round up to the next period, to the end of the current period. So we have to round to 17.75 years. So Elaine's going to reach her retirement goal of $40,000 for the beach house in the Bahamas about a year and 3 months before Jerry will reach his goal. I wanted to get this done a little earlier than possible, than we did, but I'll tell you the same thing I told my physics 20s this morning. You know, these are weird times we're in, and for the past week or so, we've kind of been doing a lot of days where we have one lesson. Well, you know, if we were in school, we have a class that's 2 hours and 40 minutes. And we only have 2 hours here. So you know the drill. You should be here for the next 15 minutes, but I'm here for an additional half hour after that. These questions deal with solving exponential equations and compound interest. You have these questions you can work on, and you have the questions from the first lesson you can work on.